Hey Level 3s, and welcome to 3.4 Atomic Structure and Bonding Lesson 5. Today's learning objectives are to define electronegativity and to describe electronegativity's periodic trend, or the periodic trend for electronegativity. Okay, here's some do now questions. I'm not going to go through these. If you've got any questions, chuck them on Teams. Okay, so electronegativity, what is it? Lots of you have used this before in level 2, so it shouldn't be familiar at all. Electronegativity, shouldn't be unfamiliar at all. Electronegativity is a measure of an atom's ability to pull on a bonded pair of electrons, bonded being the critical word here, okay? Just like ionization energy, when you're describing this periodic trend, you must include the definition. It's usually the difference between merit and excellence. A student that doesn't do the definition doesn't get E. Just like all the other periodic trends, atomic radii and ionization energy, the two things you must discuss every time are nuclear charge and the number of energy levels, remembering that number of energy levels has two subcategories, the distance, which is really the atomic radius, and shielding by inner shell electrons. Okay, let's get going. So Linus Pauling is a guy that came up with this, and this is basically a scale of electronegativity given numerical values. Fluorine is the most electronegative atom, okay, followed by oxygen and then followed by nitrogen, okay. So that's kind of worth knowing, okay. Most electronegative anyway, fluorine is probably the most useful, and that's what you learnt last year at level 2 when you were describing whether bonds were polar or non-polar. Okay, so let's discuss the trend of electronegativity. Electronegativity increases across the period, because this is the most electronegative, for exactly the same reason that atomic radius decreases and why ionization energy increases. So let's just go through a made-up example. If we're comparing magnesium and silicon, for instance, magnesium and silicon are both in period 3, therefore they have 3 energy levels, therefore shielding by inner shell electrons is going to be the same. Silicon has 14 positive protons, magnesium only has 12 positive protons. This means silicon has a greater nuclear charge, and therefore it's going to have a greater electrostatic attraction between its valence electrons and the bond, I shouldn't say valence, it should be the nucleus and the bonded pair of electrons. So we're going to change that kind of sentence slightly. So instead of saying valence electrons, okay, so we're not going to say that anymore. We're going to say bonded electrons, because that's the definition of electronegativity. So I'll repeat that last bit. So because silicon's got more protons than magnesium, it's going to have a greater electrostatic attraction between the nucleus and the bonded electrons, okay, and this means electronegativity will be greater. So that is the reason why electronegativity increases. It's always the same reason across a period, because nuclear charge is going up. So let's have a look at my model answer, template answer, and then we'll move on to the trend downer group. Okay, so I've put the definition first, always do that. No easy way around it, you just need to memorize that. Okay, bonded electrons are in the same energy level, so shielding by inner shell electrons will be the same. Atomic number increases, so number of protons increases, increasing the nuclear charge. This increases the electrostatic attraction between the nucleus and the bonded valence electrons are held onto more closely. So downer group, ionization energy decreases for the same reason that atomic radius increases and the same reason that ionization energy we're talking about electronegativity, apologies, and ionization energy decreases. So let's just pick two to discuss if we're discussing oxygen and sulfur. Okay, why would electronegativity decrease? Well, both oxygen and sulfur, for instance, are in group 16. Oxygen's got 2 energy levels, sulfur's got 3. Okay, this means sulfur's valence electrons are further from the nucleus. There's also increased shielding by inner shell electrons. This is going to weaken the electrostatic attraction between the positive nucleus and the bonded electrons in sulfur, bonded electrons because it's electronegativity, and therefore the electronegativity will decrease. Despite the fact that sulfur's got 16 protons and oxygen's only got 8, the greater number of energy levels is having a greater effect. So again, it's the same reasons and you discuss the same things every time. So we have to include nuclear charge, even though here it's not having the greatest effect. You have to discuss number of energy levels, oxygen 2, sulfur 3. You have to discuss distance, so the valence electrons are further from the nucleus than in oxygen, and you have to discuss shielding by inner shell electrons. If you can do that, you've got an excellence. Whack in a definition as well. So here's my template answer. Okay, electronegativity is the measure of attraction between a nucleus and a bonded pair of electrons. The bonded electrons are in a new energy level further from the nucleus, and there's also increased shielding from inner shell electrons. The electrostatic attraction of the bonded electrons will be less, and therefore electronegativity decreases. Don't forget to mention, despite the fact that nuclear charge is greater, it'll have less of an effect compared to the greater number of energy levels. Okay. So here's just a wee graph summarizing what we've been talking about. So here is electronegativity, and you can see here are your groups, and so you've got group 17 in red, okay, group 17, okay, and you can see that electronegativity is decreasing as you go down the group. Okay, so this is period energy level 2, 3, 4, 5, 6. So you can see the elements and it's going down. Okay, so here's a task to make sure that we've actually understood this. So it says compare the electronegativity of Na and S. Na, S. So Na and S are both in period 3, okay? Therefore they both have 3 energy levels, and therefore shielding by inner shell electrons will be the same. Sulfur has 16 positive protons compared to sodium's 11, therefore sulfur has a greater nuclear charge. This means the electrostatic attraction between the bonded electrons and the nucleus will be greater, and therefore the electronegativity of sulfur will be greater than that of sodium. In this answer, I have included nuclear charge, I have included the number of energy levels, I have included distance by saying they're in the same energy level, and I have included shielding by inner shell electrons. The only other thing we can add to our answer is whacking in a definition for electronegativity, which is the atom's ability to pull on a bonded pair of electrons, and that's an excellence answer. Okay, and that's everything I've just said. Let's do another task. This time it's beryllium and calcium. Beryllium and calcium are both in group 2. Beryllium has 2 energy levels and calcium has 4 energy levels. Therefore, calcium's bonded electrons are going to be further from the nucleus. You'll notice I've changed the words valence electrons to bonded electrons because we're talking about electronegativity. So calcium's bonded electrons are further from the nucleus, and there's also increased shielding by inner shell electrons. So this means that the electrostatic attraction between calcium's bonded electrons and the nucleus will be less, and therefore electronegativity will decrease. Despite the fact that calcium has 20 positive protons and beryllium only has 4, the greater number of energy levels is having a greater effect here. And answer's done. Okay, so in that answer, again, it's always the same reasons. I've included nuclear charge, I've included number of energy levels, I've included distance from the nucleus and shielding by inner shell electrons, and I've put a definition in. Here's my template answer or my model answer. You can have a read, but it's everything we just verbally said. Last task, and then we're done with lesson 4. Okay, this time it's asking you to talk about 3 different elements. Remember the last time we did this, I gave a hint that it's always easiest to discuss the ones that are in the same period first. So we've got F, we've got Mg, and we've got Cl. So we're going to discuss the ones in the same period first, and then we'll discuss the ones in the same group. So let's just verbally go through this, and then you can see my model answer. Magnesium and chlorine are both in period 3, which means they both have 3 energy levels, which means that the shielding by inner shell electrons will be the same. Chlorine has 17 positive protons compared to magnesium's 12 positive protons. This means that chlorine has a greater nuclear charge. This means the electrostatic attraction between the bonded electrons in chlorine and the nucleus will be greater, and therefore electronegativity will be greater. And we've justified now that chlorine has a greater electronegativity than magnesium. So now we can go on and talk about which out of fluorine and chlorine will have the greater electronegativity. Fluorine and chlorine are both in group 17. Chlorine is in period 3 and fluorine is in period 2, or you could say there instead, better is actually to say chlorine has 3 energy levels and fluorine has 2 energy levels. Okay, chlorine's bonded electrons are further away from the nucleus with more shielding by inner shell electrons. This means the electrostatic attraction between bonded electrons and the nucleus will be less, and therefore electronegativity will be less. Despite the fact that chlorine has 17 positive protons and fluorine has 9, and therefore chlorine has a greater nuclear charge, this has less of an effect compared to the increased number of energy levels. So therefore, fluorine will have a greater electronegativity than chlorine, which will have a greater electronegativity than magnesium. Hopefully that all makes sense. Any questions? Ask me on Teams. Here's my model answer. Okay, there's the first part. You can pause and have a read. And there's the second part. You can pause and have a read. Okay, team, one final slide, a bit of a summary. So we don't actually do electron affinity, so you can forget about that one. But the other 3 we do. Atomic radius decreases across a period and increases down the group. And you'll see that this trend is the opposite of the other 2. So ionization energy and electronegativity increase across the period and decrease down the group. And all of the reasons are the same. Every answer that you're doing with periodic trends needs to include nuclear charge, okay, number of energy levels, and with that you need to talk about distance and you need to talk about shielding by inner shell electrons. If you're talking about an ion, that's the one time you need to bring up electron-electron repulsion. Hopefully you're all good. Team, you've got a series of slides of NZQA questions that I've selected that are a little bit challenging, and I've gone through and written my model answers for each of them, so I'd like you to do those and make sure that you're really competent with SPDF orbitals now and periodic trends. And I'll see you very shortly for lesson 6. Thanks so much, team.